Good morning, everyone. My name is Sharanteja from CSAML branch, and today I will be talking about Jordan echelon forms, an important mathematical tool used in control system and linear algebra to simplify complex system analysis. In engineering, AI-based control, we often deal with dynamic systems like robots and drones or chemical processes that are represented by state-based equations. However, the systems can be difficult to analyze when the state matrices is larger or complicated. That's why the Jordan forms helps it converts a complex matrix into a simpler and structural form, revealing its important system properties like eigenvalues and independent modes of behavior. In short, it helps us to see inside a linear system. Introduction. In control theory, a linear system is often written in state space form as x is equal to ax plus bu and y is equal to cx plus du. X is called the state vector variable describing the system's internal condition, and u is the input vector. It controls our external signals, and y is the output vector, the measurable response. A, B, C, D, the constant matrix that describe how the system behaves. The problem is when the matrix A is large or when it is repeated eigenvalues, solving or understanding the system indirectly becomes tough. So we transform A into a simpler matrix, ideally a diagonal one. But sometimes diagonalization is not possible. In those cases, we use Jordan echelon forms, in which next best thing to a diagonal matrix. What is Jordan echelon forms? The Jordan echelon forms are also called Jordan conical forms. It is a special kind of matrices forms that organize a matrix into a simpler box. A matrix A is said to be an Jordan form if it can be written as J is equals to J1 0 0 and 0 J2 0 and 0 0 J3, where each Ji is a Jordan block corresponding to one eigenvalue. A Jordan block looks like Ji is equals to lambda I 1 0 0 and second row 0 lambda I 1 0. Third row double zero and lambda I 1 and fourth row triple zero and lambda I. Here lambda is the eigenvalue repeated along the diagonal. The ones above the diagonal represents the generalized eigenvector linking together states that share the same eigenvalue. If every eigenvalue of A is distinct, the matrix is diagonalizable, meaning it's a Jordan form. It is simply a diagonal matrix. If some eigenvalues repeats or A isn't diagonalizable, the Jordan forms shows us how much coupling remains between the states. Why Jordan forms is usable. Let's see why we need Jordan forms at all. Simplifies the system dynamic. It breaks a complex system into a smaller, nearly independent subsystems, Jordan blocks, each presents, presenting one mode of motion and oscillations. And it also reveals eigenvalues and system modes. It means the eigenvalues tells us about system stability, whether the system will settle, oscillate or diverge. Useful for control designs means many control techniques like state feedback and observers and model analysis become easier ones. The matrix A is in the Jordan form helps us in solving the different equations. For example, to find it's much easier if A is Jordan form because it can be computed into block by block. In short, Jordan forms the matrix more systematic and modular and unpredictable. Linear state transformation. Now, how do we actually use the form in a state transformation? We perform a change of variables x is equals to capital T z, where T is an transformation matrices made from eigenvectors and generalized eigenvectors, and z is the new vector in the transform coordinates, where we substitute x is equal to tz into our system equation. So x is equal to az plus bu. We get tz is equal to atz plus bu, and z is equal to t inverse minus 1 atz plus t inverse minus 1 bu. Now t inverse at is equal to j, which means Jordan form of A. So we transform system becomes z is equal to jz plus bu. This version is simpler to analyze, stimulate or control because J is simpler and its block diagonal or nearly diagonal. Sometimes we also transform the input V to y inverse is equal to T inverse U to simplify the control input equations. This is known as input transformations. These transformations don't change the physics of the system. They also just give simpler mathematical viewpoint. Input transformations. Steps to obtain Jordan echelon form. Here is how we compute the Jordan form in practice. Find the eigenvalues of A by forming A minus lambda I is equal to 0. In second one, for each eigenvalue, find the eigenvector. In third one, if you don't get enough nearly independent eigenvectors, find generalized eigenvectors that satisfy A minus lambda I is equal to V is equal to 0. Arrange all the vectors and generalize eigenvectors into a matrix T. Compute J is equal to T inverse AT. Verify that J has block diagonal structure with Jordan block. For example, if A is equals to if for example A is equals to 4 3 2 3 x plus 1 0 u. The eigenvalues lambda is equals to 5. So only one linear independent eigenvector exists. So y is equals to 1 0. A generalized eigenvector v2 is 0 1. T satisfies the a minus phi I v2 is equals to v. The Jordan forms A is j is equals to phi 1 0 5. Interesting this, a matrix is already a Jordan form. This tells us the system has one eigenvalue phi, but two states are linked. They cannot evolve independently. Advantages. Let us summarize the key benefits of eigenvectors. It simplifies the system analysis and separates independent dynamics. And also, it helps us to identify the controllable and uncontrollable modes, crucial for control system design. It's also useful in observer design, especially when estimating internal assets. And also it makes mathematical operations simpler, like finding uh, finding E8, solving different equations. And also it reveals system stability and natural behavior through eigenvalues. Applications. Control system design. It gives state feedback and store placement and robotic automation modeling, signal processing and system identification. And another is stability analysis in AI control system. And summary and conclusion. To conclude, Jordan forms converts a matrix into a structural block diagonal form, revealing its fundamental properties. The transformation is x is equal to tz, simplifies analysis without changing the physical meaning. Steps: finding eigenvalues and finding eigenvectors and generalize eigenvectors from form T. Compute J is equal to T inverse AT. So, Jordan form is a powerful tool in linear system theory. It also allows the state and input transformation very easier analysis. And steps: eigenvalues is equal to generalized eigenvectors. To the next transformation matrix and next transformation system. It specialized control design and stimulation. So at last, steps to derive Jordan forms. Find the eigenvalues, solve A minus lambda I is equal to 0. Find the eigenvectors of each eigenvalue. Find the generalized eigenvector if we need when the matrix is diagonalizable. Form the transformation matrix matrix T using all these vectors. Compute J is equal to T minus A1 AT. This is a Jordan echelon form. So the Jordan echelon form transforms complexity into clarity. It allows engineers and mathematicians to see what each part of system behaves independently and design controllers more efficiently and analyze system stability in structured mathematical way. So Jordan forms is a simpler view of complex systems. It is a bridge between the abstract linear algebra and practical algebra analysis. So thank you.